Professor Hassan Mahmoudi from الشلف University. The session chairs Professor موفق بن علي from سيدي بلعباس University and Professor كرفاح رابح from خميس مليانة University. Professor Mahmoudi, you have 40 minutes.
Thank you very much. بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين. السلام عليكم ورحمة الله تعالى وبركاته. So it's my pleasure today to be with you. Let me first thank the organizing committee for giving me this opportunity to be with you and to present this keynote entitled Desalination and the Renewable Energies Between Challenges and Ambitions. Well, all of us know that water is life. And if we want to know the amount of water on the surface of the earth is more than 70%, and only 30% is lands. But the problem is that how much drinking water is means the ratio of the drinkable water in this global water amount. We can say that drinkable water is not such big amount, because if we analyze the global amount of water in the earth, 97.5% is saline water, which means we cannot use this water directly. And only 2.5% is fresh water. The amount of glaciers and ice from this 2.5 is 68.9, which means that we cannot use this water directly because it's ice, it's solid. We have to put energy to melt this water before being used. And we have 30.8 groundwater, which means we need energy to pump this water from the soil, so we cannot use it directly. Only 0.3 is lakes and rivers, so we can use it directly. So from the 100% of fresh water available on Earth, we can use only 0.3%. So this is just a little amount of fresh water. So what is the solution for that? So the solution is, let's say, it's not easy, but the theoretical solution is to transform part of the saline water, which represents more than 97.5%, into fresh water. This is the way how to produce more fresh water. So to understand how we can do that, we can take a cup of water and we put salt till we get a high saline water. Let's say till 60 or 65 or 70 grams per liter of salt. So this is high saline water. We can call it also concentrate. And in the other hand, we take a cup of water, which is fresh water or distillated water, where the concentration is more or less zero. If we mix the two cups, means the saline water with the fresh water, we can have a new cup with a low salinity than the first one. And this is also a saline water, but with reduced salinity. So we can say that the first one is highly saline water, is a concentrate. Let's say the concentration is 60 grams per liter. The second one is distillated one, is 0 grams per liter. And the third one is 30 grams per liter. This is approximately. So this is a mixture of two kinds of waters, one saline and one fresh. If we go from the bottom to the top, means if we have a saline water, which is seawater with a concentration of 30 grams per liter, it is normally possible to have in one hand a high concentrated water, which is the concentrate, and in the other hand, a distillated water. So the first operation is a mixture, but the second operation is a separation. And in chemical engineering, we know that for any separation technique or method, we need energy. And this is the bottleneck. So if we have raw water, we can get from this raw water fresh water, which is distillated, and high concentrated water, which is a brine. This is from the bottom to the top. But we need for that a separation process, and this separation process needs energy. So the energy can be heat, we can heat water, and can be also electricity. Normally the process that let us produce fresh water and concentrated water from saline water is called desalination. So please, desalination is not the operation of taking out salt, but taking out fresh water. This is very important. So if the process uses electricity, commonly it's named membrane processes or membrane desalination. And if the process uses heat, it is thermal processes. So let's see some examples of these processes. For example, for thermal processes, we have the MSF, which is the multi-stage flash distillation. We can see this is a MSF plant. We have also MED process, which is multiple effect desalination, or distillation, sorry. So this is the MED. For the membrane process, the main or the common or the most known process is the reverse osmosis process. This is the reverse osmosis process, which use membranes and modules. And we have also electrodialysis, ED. So this is the main processes we use for desalination. There are more than that, but the main one are MSF, MED, and reverse osmosis, and electrodialysis, the most used in desalination in the world. So for desalination in the world, we have to see some scenario. As Professor Shaib talked today about scenario 2030 and scenario 2050, we'll talk about scenario 2030. If we analyze the first figure on the top, it represents the water stress for the scenario 2030, and the water stress is known as the ratio of the total water demand in the region to the annual renewable energy, or renewable water, resource available in that region. And for the figure in the top, as I told before, it illustrates the regions in a global water stress. So if we can localize the regions where we have a global stress, we can imagine that these regions needs solutions, and among these solutions, we propose desalination. So for the second figures, it's the resulting global desalination demand is presented in the second figures, and you can see easily that, I don't know if it is clear or not, the region of Algeria, which represent a big demand for desalination plants in the bottom, of course. So nowadays we estimated 15,000, or let's say 16,000 desalination plants in the world, and it is located in more than 177 countries in the world, and the global desalination capacity in the world is about 104 million cubic meter a day. It's huge. If we see which kind of process we use the most in the world, we can see that reverse osmosis use 62%. I don't know if it is, no, this is 58, but the most recent statistic shows that it is 62% of the total capacity is produced by reverse osmosis. And 27% of this is produced by MSF. As we said before, MSF, RO are the most, and MED are the most common process used in the world. And for the water, as we can see, for the water, 62% of the water is seawater. So that means that the most important, all the desalination plants are situated in the coastal line, so that use directly raw water from the sea. And 19% is brackish water. So brackish water is just after the seawater, and brackish water we can find it in the ground or in albions. Now, how about desalination in Algeria? So Algeria, as you know, is the largest country in Africa. It was the second, actually, is the first. It was after Sudan, and now Sudan is divided in two, maybe more in the future, who knows. And Algeria, alhamdulillah, is the first and largest country in Africa. And more than 4/5 of its surface is desert, as you know that, where rainfall is approximately zero. There is no rainfall. The northern part of Algeria is less stressed, and it is also facing drought problems. So for that, the government was obliged to find a solution to this problem of water shortage. So as you may know, in the early 2000s, water shortages were so strong and caused a capital riot of thirst. We remember all that. People were waiting for water in their houses for long hours, and there were no water, no fresh water. So the unique solution at that time to resolve this problem was desalination. So for desalination, the program was established in many stages regarding the problem and the region and the nature of the problem. So the first program was the program of the northern part, where approximately 80% of the inhabitants lives there. It starts with the small desalination plants with a maximum capacity of 5,000 cubic meter a day. So these plants were situated in big cities were facing high water shortage. So it was the first program, just small desalination plants in all the coastal line, and especially in cities where the problem was important. So the second stage was dedicated to the big desalination plants, called the XL desalination plants, X large desalination plants, and the capacity started from 1,400 cubic meter a day to more than approximately 500,000 cubic meter a day. So 13 plants, X large plants, were constructed along the coastal line, which extend to more than 1,400 kilometers. So in these figures, you can see all the desalination plants in all the region, in all the coastal region. You can see that in each big city, the government constructed a big desalination plants to cover the need for these regions. And also, it is important to notice that in Mostaganem, the largest RO desalination plant, which is Makta, it is 500,000 cubic meter a day. It is very huge. 1 cubic meter is 1,000 liters. And when we say 5,000, you can imagine how liters. You can imagine how bottles of water are produced every day. So this is very, very, very huge. So the first program was for the southern part, and the second program was dedicated to the southern part. Okay? Even if in the southern part that we have not a big population there, only 20% of the population, but the government have to cover the need for water for this region. So after resolving the problem fresh water in the northern part, where live more than 80% of the population, the government decided to go ahead and resolve the problem in the southern part. For the southern part, the good thing that we have a reservoir, a big reservoir, which is called the Albion Reservoir, and this Albion Reservoir covers an area about 1 million square kilometer. It's very huge, 1 million square kilometer. You can see in the map how large is this Albion, and this this aquifer is shared between Algeria, Tunisia, and Libya, and the basin contains approximately 60 trillion cubic meter, 60 milliards de mètres cubes. 60 milliards de mètres cubes. And the highest temperature in this Albion reservoir can easily reach 80 degrees. La température peut facilement atteindre 80 degrés, avec une salinité modérée, une faible salinité avec une température très élevée. So we can use constructed 12 plants in different places in the So, unfortunately, desalination is not the magic solution for the problem of shortage of water. It is not a magic solution. It has the advantage and disadvantage. Because it is a high energy consuming process, water demand rises, and oil and gas reserves deplete. This is the problem. The problem that's, for example, in Algeria, we need more and more water, but in the other hand, we need more and more energy. But the bad scenario that our reservoirs of gas and petrol are depleting. This is the problem. So we need to desalinate. We need to produce fresh water, but we cannot ensure the energy for this desalination plants. So the consequence is that we are going quickly to something very bad, which is the peak oil. We will not have enough oil and gas to how to say, for our own needs. We will not have enough gas and oil for our own need. So when energy is available, it generates greenhouse gases. So even if we have energy, if we have gas, if we have petrol, when we produce energy, electricity from gas, we are producing CO2 and we are polluting the atmosphere. So if we have and if we have not, it will be a problem. So what is the solution? What is the case? The case are that the price of desalination can decrease, can increase when water need will increase, because if we will not have enough energy resources, so the price of the desalinated water will increase dramatically. So if we see the scenario we saw before, if we have a raw water, we can produce, as we see before, fresh water and brine using a separation process and using also energy. The challenge is desalinate more because the population is growing and polluting less. This is the challenge. How to produce fresh water, more fresh water, and how to pollute less. Means we not be able to use energy as we are doing now, because we are polluting a lot. So the solution is the using of renewable energies in desalination. If we use renewable energy in desalination, we can reduce dramatically the pollution, the atmospheric pollution, regarding the fossil energy. So using renewable energy in desalination can be in two different ways. The first way is using renewable energy as energy supplies. Means we can have photovoltaic park, we can have wind park, we can have whatever we think. We can produce electricity and take this electricity and go to the desalination plant, and it's easy. So using renewable energy as energy supplies. The second scenario, which is the most important one at least in my point of view, is using renewable energy as part of the desalination process. It is a part of the desalination process. So it means the process itself use renewable energy in its process. If we can analyze the possibility of using renewable energy sources in desalination. So possible combination, as you may see in this figure, of integrated system. So we can use renewable energy for AD, which is absorption desalination, which is direct use of renewable energy. We can use it also for electrodialysis by producing electricity and using this electricity in electrodialysis. We can also use it the renewable energy as source of electricity in EDR, which is electrodialysis reversal. We can use renewable energy for the humidification, dehumidification processes, which is the second scenario. The renewable energy is a part of the process itself. We can use it also in membrane distillation, which is also means the desalination. Means renewable energy is a part of the process. We can use it as in multi-effect distillation, in MSF, in MVC, which is mechanical vapor compression. We can use it in RO directly. In RO, we can produce electricity, and then this electricity can power the reverse osmosis desalination plant. So let's see some state case studies to understand well how we can use renewable energy in desalination and at X large scales, not at laboratories. So the first one is using renewable energy for energy supplies. Is it possible to produce electricity from renewable energy and use this electricity as a power for desalination plant? The best scenario we can present for you is the Perth desalination plant in Australia. So for the Perth desalination plant, the seawater, we can see this diagram. This is very important. This means that we can produce electricity from wind, from photovoltaic, and then take it directly to the network, and take out the electricity from the network to the desalination plant, and this desalination plant can use this electricity to power means we can use this electricity to power the reverse osmosis plant and produce electricity. I will show you in figures. The example of that is the Kwinana reverse osmosis desalination plant. The Kwinana desalination plant is situated in Perth in Australia, and this is the desalination plant. And this desalination plant is powered by a wind farm of 48 turbines situated 260 kilometers far from the desalination plant. And this is very important. If you have a desalination plant in the coastal line, that don't mean that you need to have a park, a wind park or photovoltaic generation electricity near the desalination plant. You can have it far. For example, for the Perth desalination or the Kwinana desalination plant, we have the desalination plant, and the wind park is situated 260 kilometers. Il est situé à 260 km loin de la station de dessalement. Donc, on n'est pas obligé d'avoir l'installation du parc éolien ou la photovoltaïque juste la station de dessalement. On peut l'avoir ailleurs. C'est-à-dire, on produit de l'électricité, on injecte l'électricité dans le réseau et on utilise cette électricité du réseau, et ça peut compter comme étant une énergie renouvelable parce qu'elle a été, à l'origine, c'est une énergie renouvelable. So this is the case of Kwinana desalination plant. So you can see that even if it is 140 cubic meter a day, it is similar to the Hammer desalination plant. It practically is the same thing. So this desalination plant can be enough for a capital like Algiers. And it is fully powered by wind energy, which is situated 260 kilometers far from the sea. For the second case, means renewable energy as part of the desalination plant. This is different. Means that the renewable energy is directly used by the process. The best choice is the Professor Shaib is more experienced in that. The greenhouse desalination plant, for my point of view, is the best choice for the to explain how can renewable energy be used directly in a desalination process, which can be used for the projection of fresh water for irrigation. And this is very important for case. We'll see later how it's important. So as you may know, fresh water for irrigation represent more than 80% of the consumption. And this is very, very, very important. Means if you produce 100 liters or 100 cubic meter, you should know that 80 cubic meter is used for irrigation and only 20 for for the for drinking processes. So the freshwater sources are finite. There is a relentless pressure to reduce agricultural use of water. As you may know, in many parts in the world, we use big parts of water for irrigation, and this part is commonly it's approximately 80% of the total amount. So if we can imagine a desalination process which can produce fresh water for irrigation, we will resolve the problem. So if we ask the question, what is the solution for that? I think it's easy to answer. It's desalting water for irrigation. But how? How desalting water for irrigation? For irrigation, we don't need high quality water, because there is for the les normes de l'eau potable et les normes d'eau d'irrigation sont différentes. C'est-à-dire on peut produire une eau d'irrigation avec une qualité inférieure à la qualité d'eau potable. Donc on peut imaginer un système de dessalement qui peut produire de l'eau à des raisons agricoles, l'eau c'est une eau à qualité inférieure. Donc desalting water for irrigation is easier than desalting for freshwater purposes. So a possible solution for this dilemma means sea and brackish is the sea or brackish water greenhouse desalination. This is, if you can see, this is not a normal greenhouse. This is a greenhouse which is we have three components. We have three components. You have the first one, the second one, and the third one. To well understand, it's very easy. The process is very easy. Here in the front, we have a humidifier. Un humidificateur, c'est très simple. C'est un système à nid d'abeille. Donc on fait introduire de l'air chaud, et on alimente avec de l'eau froide. À la sortie de l'humidificateur, on a de l'air chargé, de l'air humide chargé. Okay? So we have a humidifier here, and we have a second humidifier just here, because from this point to this point, if you have a plantation area, the area will should use an amount of humidification. The plants will use, so the humidity will decrease. So we need a second humidifier here, and we have in this point a condenser which can take this humidity and produce fresh water for irrigation. So the planting area here between the first and the second humidifier, and we have some tanks for salty water and from fresh water. So this system can produce fresh water for irrigation. Not of very high quality fresh water, but it is enough for the irrigation purposes. This is the process. It's very easy. So we have hot and dry air, which is ideal for Algeria, for example. If you go in the southern part, the simple or the easiest thing is to find hot and dry air. This is not difficult. So the hot and dry air enter this humidifier, and here the humidifier we have water, droplets of water. The contact between hot and dry air with water will produce humid air. Here in the second humidificator, it is the humidification is increased, and we can take out the water from using the condenser, and this water can be used for the irrigation. So this is a compact desalination, compact greenhouse with a desalination process using humidification, dehumidification. So the most important thing is the analysis of the water consumption, inside and outside the greenhouse. If we see outside the greenhouse, for the same agriculture species, we use 8 liters per square meter per day. But if we use this greenhouse, inside the greenhouse, it produces fresh water, and also it offers a good environment for the plants. We use only 1.2 liters per square meter per day. So we reduce the consumption of water by a factor of 7, and this is very important. So we reduce the consumption We produce the fresh water for the irrigation, and we help people to establish in a rural area with less fresh water. If we take this possibility and see how can this SWGH be used in the southern part of Algeria, because in the southern part of Algeria we have the Albion aquifer with a high salinity, not a high salinity, but a medium salinity, but we cannot use it directly for irrigation. And we have dry and hot air, so we can use this technology. So if we use this technology in the southern part of Algeria, it's very easy. We can pump water from the Albion. This water is hot water, which help more to get the air more humidifier, and we use this humidity inside the greenhouse, and we produce fresh water in the condenser, and we use it to irrigate the greenhouse, the planting area inside the greenhouse. As we said before, the temperature in the aquifer Albion can easily reach 80% degree, so we can use it directly here for the projection of fresh water using MD. The MD is the membrane distillation, and membrane distillation is very easy process which can produce fresh water from moderate, let's say, high water. It means 80 degree. It's very good to use in membrane distillation to produce fresh water. So if we are near the Albion aquifer and the temperature can reach 8 degrees, we can imagine that the greenhouse can have the humidifier and the condenser, and also a membrane distillation device or membrane distillation part which can produce fresh water for irrigation. This is very important. So if we use this technology in our desert and in the Sahara, we can imagine that our desert can be Sahara, but a Sahara forest. Everything can be green if we can use this technology. It's very easy, simple, and environmental friendly process. We are allowed to dream. Hein? On peut rêver. C'est pas interdit. Now, combine renewable energy driven low energy desalination process. How we can use renewable energy with a desalination process to produce fresh water. We have two big families. We have our two big processes, two important processes. The first one is the adsorption distillation, AD. The adsorption distillation AD cycle produces two useful effects. One, high-grade potable water. We can produce a very good potable water. And in the second hand, we can produce cooling. On peut produire du froid, et on peut produire de l'eau potable. Donc ce système, qui est la distillation à absorption, peut être utilisé à des fins, c'est-à-dire on peut produire de l'eau et on peut produire du froid pour des raisons sanitaires. The second process is the membrane distillation, MD. And the membrane distillation, MD, is a thermally driven desalination process which utilizes a hydrophobic microporous membrane. It's very easy also. You have a membrane, and this membrane is hydrophobic. If you have a high temperature, so the water at high temperature, the vapor can go through these pores and be taken from the other side and condensated. And by the way, we can produce fresh water. So what are the main advantages of membrane distillation or adsorption distillation? The first one, they are simple. They are very easy to understand and very easy to use too. They operate at low temperature, which means you don't need to heat water to 200 or 300 degrees. 60, 70, 80 is perfect. which means you can take directly water from the Albion reservoir and go directly toward the MD or the AD desalination plants. So these two kinds of desalination plants can be easily used for the southern part of Algeria. Also, the system is compact. It's not large one, it's compact one. And it is also scalable, which means you can have a desalination plant for, let's see, if we need 100 cubic meter, we can have a desalination plant of 100. And if we need more, we can use directly. It's scalable. This is an absorption desalination with cooling prototype from coast, but then you can confirm that. And this is a solar flat plate which is used for this AD. So you can see that we can use both in renewable energy and desalination plant together. This is at cost, nothing. So the conclusion of what we said, there is a necessity to find an equilibrium or compromise amongst the three sets of aims: social, economic, and environmental. Social, economic, and environmental. If our decision makers are not convinced of what we are saying, we cannot change. So my keynote today, de rester chez soi et dire que le gouvernement est en train d'investir et tous les investissements qu'il a faits sont des investissements polluants. Non, le scientifique ne doit pas critiquer, le scientifique doit proposer des solutions. Il doit parler, discuter jusqu'à ce que le décideur, le politicien prend comment dirais-je, la bonne décision. So, let's say that large-scale deployment of renewable energy in desalination is very dependent on economic and political influences as well as environmental and social factors. You can see that political influences is always there. Le scientifique ne peut pas prendre une décision sans avoir recours aux politiques. Ils doivent travailler ensemble. Et ça, c'est très, très, très important. Sur ce, je vous remercie pour votre attente et je m'excuse si j'ai pris beaucoup de temps. Merci.
Alors, merci, professeur.